5.6 is the last section in chapter 5. It goes hand in hand with the section, I think it was 5.2 when we did exponential functions, and we were compounding, I don't know, monthly was our n was 12, semi-annually our n was 2, and so forth. But what if you compounded every single second? That's exponentially. So this is a population growth function, guys, that can be used for many things. So it can be how fast certain populations grow, whether that's humans, rabbits, bacteria. It can be how fast our bank account grows, or hopefully not your debt grows. So I know, right? So let's look at everything's labeled for us. So in the function p sub 0, it's called p naught. That's the population at time 0, aka the starting amount. And then p of t, the left side, is the population at time t, so your accumulated amount. T is the amount in time in years. K is your exponential growth rate, whether that is a growth rate for repopulating or an interest rate, whatever it may be, okay? So it has to, oh, I guess that doesn't have to be in years. So I typically we're going to do years, and so this would be per year or whatever. So it just has to have the same unit as time. So I guess the unit doesn't have to be time, years, but everything we see will be years. Okay, let's look at the graph. This is going way back to section 5.2. Remember, the graph of a exponential function looks like this, where 0, 1 was always a point. Well, it's going to be 0 p naught, your initial amount, right? And then we're going to grow exponentially after that. So let's look at example 1. We have in the year 2011, the population of Mexico was about 113.7 million people. And the exponential growth rate was 1.1% per year. So it says find the exponential growth function. So we're going to write this generic function, p of t equals p sub 0, or p naught, e to the kt. So we're going to start with the generic, all right? And you should be able to fill in p naught and k. E will stay there, t will stay generic, okay? So we have p of t equals p naught e to the kt. So p of t will stay here because this is supposed to be the function for population at any time t. What's our p naught? Well, if you go up here, the p naught was the starting amount. What starting amount were we given?
The million.
Yeah, and we won't put a bunch of zeros. We'll just use 113.7, and then our answer will say million when we get done doing it, okay? So this will be 113.7. E raised to the kt is part of the function, but what is our k?
1.1.
And we got to put that into decimal form. So let's make that a note up here. K should be in decimal form. So this will be raised to the 0.011t. There's your function, and that's all they're wanting. My 7's a little large. It doesn't need to be any larger than any other number, but okay. So what's the point of this function is I could say, okay, guys, it's the year 2019. How many years past 2011 is that?
8.
8 years. So what would you put into it for time t?
8.
8, and you'd be able to figure out the population now, okay? So they'll have us do that, but before we get there, they have us graph this. This is something I want to play around with. I'm not too sure, like, how specific it wants. But we're just going to mimic this graph, and all we can really do is mimic that graph, but instead of p naught, put the starting amount, okay?
So say if it was 8 years, you would put that instead of the pt?
No, you put p of 8 equals, and you plug 8 in for t.
Oh, okay.
And you would be finding p of t, okay?
Oh.
So this is going to be our t-axis. This is going to be our population axis, and we're going to grow exponentially, so our function looks like this. The question is, what is the starting point? Well, what was the population at time 0?
113.
Yeah, so that's kind of all we're labeling.
Say that fast.
So when you guys do this, I believe, and I'll double check, but I'm pretty sure it might be a multiple choice graph. So pick the right shaped curve going in the right direction, and then make sure your y-axis, but technically this is called the p-axis, it's the population axis, it's crossing out your starting amount, okay? So notice what it asks us. It says estimate what the population was in the year 2015.
That's 4.
4, exactly. So the t equals 4. So they're asking us to find p of 4, which means anywhere you see t in your function, plug 4 in. So we have 113.7 e to the 0.011 times 4.
I have my calculator.
Yay! And that could be in parentheses or however you need to do it, depending on what calculator you have. I think mine's older, so when I do the caret button, it doesn't put me up into the exponential. There, I'm trying to get it so you can read it. Okay, so we're going to type 113.7, and then the e with the caret is already kind of down here over your natural log. So we'll hit second natural log, and it automatically brings that up, and we'll just close it off by doing 0.011 times 4. And you hit enter. Since this was rounded to 1 decimal, we're going to assume that this is rounded to 1 decimal, and then we'll put million, okay? So P of 4 should be 118.8 million. Is that okay?
Yeah.
So it grew about what? 5 million? 113, okay, roughly. All right, so the next part, this double idea, you see it a lot. You see it again like in growth of decay, not growth of decay, that's the opposite. Growth of bacteria and so forth, where they want to know, okay, at one point has it grown double? So there's a couple ways to do it. If they give you a starting amount, 113.7, then it's easy to figure out what double means, right? What's double 113.7? Just times it by 2, okay? So, but what I want you to notice, and we'll do it kind of both ways, but we'll do it with theirs. So they are giving you the accumulated amount. They're giving you the left side. They're saying, okay, at what point do we have double what we started with? So what's 113.7 times 2? 227.4. So that is the P of T. And so then the right-hand side, we're still using this generic equation over here. The right-hand side is what? 113.7 e to the 0.011 t. Is that okay so far?
Yeah.
So they might say, at what point has it tripled? And what would you do over there? 3 times whatever your starting amount. Or what time? At what point is it 1.5 times? You know, they'll give you numbers, and all you do is multiply your starting amount by that amount, and that's the left side. So then this turns into an exponential function that we solved yesterday. We want to eventually get t by itself. He's up in the exponent, so we're going to eventually write him as a log. But before we can write him as a log, the exponential part, the base in the exponent, has to be isolated. And who's in our way right now?
227.
Well, he's by himself. We want to get we want to get him by himself.
Everything else.
Who's
The 113.
So how are we going to get rid of the 113.7? Divide both sides by that. When you do that, guess what you're going to get on the left side? 2. Does that make sense? Yeah, because that left side was double the amount. E to the 0.011 t. This is what I'm talking about. No matter what, even if they didn't give you your starting amount, any double problem, you can go right to this. Because you know that your P naught would just divide over and you'd have 2 times your P naught over there, okay? So no matter what, so I think we see one like that on our worksheet, and I'll point it out. Even if they didn't give you a starting amount, your doubling formula, you can go right here, okay? Because double means your starting amount was 1, we double it to 2. It will work no matter what. Okay, so how do we get the t down? We need to write it as a log. So I always say, what's the base? E, so how do we say log base E? Natural log of what? The opposite side, no, 2, equals your exponent, which is what? 0.01 t, 11 t, right? 2 ones. So what's the log? It's base E, so it's natural log of the opposite side 2 equals your exponent. Remember, your exponent is another way to write log. So how are we going to get t by itself? What do we need to do?
Divide.
Yep, so we'll have t equals the natural log of 2 all over 0.011. I'll put the squiggly brackets. It's not an exact number, guys. So again, when you put it in your calculator, you just have to be careful. Make sure you close off the natural log of 2 before you divide. I can never get that in there so you can see it. Okay. So we're going to do natural log of 2, close it off, divided by 0.011. You hit enter. It's approximately how many years? 63 years. So it will take Mexico 63 years to double its population from 2011. So what would that be? Year 2074 or whatever. You can answer that. Are there any questions on that front page?
No, I like it.
I think it's cool. So then the next page is just the same kind of function, the same kind of idea, the same questions, but now instead of it representing population growth, whether that's humans, bacteria, bunnies, it's representing your account growth, okay? It's doing money. But notice the formula looks very, very similar, okay? So P of 0 is your initial amount, right? Starting amount. You don't have to label this again if you don't want. It's all kind of the same thing. P of T is the balance after so many years, so it's your accumulated amount. I'm going to label everything the same. T is your years, K is your interest rate, compounded continuously in decimal form. And we're going to do exactly what we did on the front page. They're going to ask us a couple questions, and we're going to be able to plug things in to get some stuff. We have a little bit more work to do. So let's read what's going on. It says, suppose that you invest $2,100 at an interest rate of K, so we don't know K, compounding continuously, and it grows to $2,504.65 after 5 years. Let's first find the interest rate, okay? So what we have to realize is you're going to always be given everything but one variable, okay? So you might be given P naught, K, and T, and you can plug it all in to find P of T. Or you might be given P of T, P naught, and T, and you can plug it in to find K, and so forth. So we always have to plug in what we know. So what's this $2,000 represent?
PT.
Starting amount.
It's the starting amount, right? That's our P naught.
Yeah, no.
We don't know K. It's compounding continuously and grows to that. What is the 2,500?
The accumulated.
Yep, so that's going to be our P of T, right? And then what's the 5 years represent? The time, okay? So notice we can plug in everything and the K's are just going to stay constant, right? So the P of T, the 2504.65 will be on the left side of the equals. The P naught, the starting amount of 2,000, will be on the right side. It's compounded continuously, so that's why we know it's going to be E raised to the K times T power, but that's just 5. And how we solve this, guys, is going to be exactly like how we just solved the other one. We want to get E isolated so we can eventually write it as a natural log, okay? But so divide by 2,000 first. So when you do that, guys, we do not want to round, okay? So if you want to write all that out or leave it as 2504.65 over 2,000, because the earlier you round in this problem, the more off you're going to be, okay? So when I did this, I know it's kind of a long decimal, but we're going to write it. It's 1.252325. And then I'm going to rewrite it as 5K instead of K5. Is that okay? Because we just like to write a coefficient front. So 2,000 went into that a little bit more than once. All right, so how do I get my exponent down? I need to write them as a log, right? So this is log base E, but what's really log base E? Natural log of what? The opposite side, 1.252325, equals your exponent, 5K. Are you guys kind of getting the hang of that? That's something that we just got to do over and over again. It's 5.3 over and over again, writing that log, going back and forth.
And then you
Divide by 5. So K, as weird as it looks to write down, is going to be the natural log of 1.252325, all divided by 5. Let's say it is 3 decimals, I think. So I will do that with you. I already have it there, so I'm going to do the natural log of that, divided by 5. So what is that going to be? 0.045, do you agree? Don't worry about the rest of it, okay? So this is going to be 0.045. But if they're asking for K, they're most likely wanting it as a percent, right? So what would that change to as a percent? 4.5%. And that looks reasonable for an interest rate. But now that we've done all that hard work and found K, we can go back to our generic equation, plug in our P naught and plug in our K, and just come up with the exponential growth function, meaning leave P of T alone, leave T alone, let's plug in everything else, okay?
But you do it the 0.0.
But we have the K now, exactly right. So we're going to do P of T equals our P naught, but what's our P naught? 2,000 times e to the kt, but what did we just calculate K to be? 0.045 T. There's your generic exponential function. So now I can say, oh, I've been investing for 1 year, 2 years, 100 years. You can plug in any T and figure out what that accumulated amount is. So whenever they ask for the function, guys, that means they want your variable to stay a variable, right? Like leave T there. Leave T there. Because here in part C or D or whatever, we're going to be plugging stuff in, and then that's when we actually have a value. So if they want the function, they want that T there. All right, so C says, what will the balance be after 10 years? So what do we need to do?
Use T as 10.
Yep, so we're finding P of 10. So we'll do our P naught, which is 2,000, times e to the 0.045 times 10. So just plug that in your calculator. It's kind of dark, I know. But we'll do 2,000 times second ln to get me my e with my exponent, 0.045 times 10. And what's it going to grow to? It doesn't tell us what to round to, but it's money, right? So money's always rounded to the nearest cent or 2 decimals. So what's behind our 62? Just a 4. So that will just stay 62. Yep. So after 10 years, guys, our investment, P of 10, will be $3,136.62. So about 1.5 times. That's not too bad. All right. So D is just kind of like what we did at the front. It's like, I really want this to double. I need $4,000 because I want to buy a car. I need that money. How long will it take $2,000 to have doubled? Well, again, they're asking for how long, so we don't know T, but we know our initial amount, and we know doubling will give us a what ending amount? What will be our ending amount? What would be our 4,000, right? Doubling that will be 4,000. But what's the first move we're going to make before we try to isolate T? Divide by 2,000 and see what happens when you do that. See, and remember how I had you star that right over here? No matter what scenario you have, doubling it will get you to 2e to the point whatever, right? So when I divide by 2,000, I know I'll always have the 2 on the left, and then my initial will always cancel out on the right. And so I just have e to whatever my exponent is there. All right? So how do you solve for t? We need to get him to come down to earth, and that's what natural logs are, right? So log base e, or natural log of what?
2.
2 equals what?
0.045.
T. And then how do I solve for t? Take the natural log of 2 and divide by 0.045. And it's always kind of an approximate. Oops, I'll go this way. Again, it's kind of dark. So we'll do natural log 2, make sure you close off your parenthesis, divided by 0.045, approximately 15.4 years. And then just round to whatever they tell you to. So I'll do my squiggly brackets, 15.4 years. So you might want to go another route, because I don't know if you can wait 15 years to get that car.